So that's coming through my computer, which could work.
Yeah.
What's that?
This is what we did before.
Audio here, screen here. Okay. Go ahead and test if you would.
Test.
Online people here.
Can you hear me? Online people?
Oh, that sounds promising. So that's coming through my.
That's a lot.
That's the.
Okay. Well,
let's move forward.
Let's just keep trucking. So yeah, just to reiterate, I'm definitely not an expert in these things. I've just used them in a pretty basic sense. So those of you who have used them more, feel free to pepper in comments or questions. So yeah, again, let's try to keep this interactive and helpful for everybody. So just looking through like what are regex, regular expressions, they're called, shortened to regex. They're just basically a simple ways to find patterns in text.
Hey Steve.
Yeah.
He's not broadcasting his screen, is he? On your Google Hangout. We flip over to your Google Hangout and hit screen share.
But there is about a 15-second lag.
If only there were anyone here who knew about computers.
Yeah, why is it not?
I don't know. I can't imagine I need to share my screen. Let's try this.
Who's hosting?
Oh, there we go. That'll probably help with it.
Oh well, it's in the background.
Yeah, maybe we can like point it towards that.
Okay, we'll mess with that for next time.
Okay, yeah, sorry about that.
No, it's my fault.
Okay, so again, it's basically we're just messing with text. We're matching patterns in text. We're manipulating it with regex, regular expressions on a basic level. This is a tool that is used across platforms, so it's something that's helpful to learn. I think it's a good tool in your tool belt because you can use these in Python or shell languages, things like that, and I think they just speed up workflow a lot. So how do they work on a basic level? What you do is you start with a string, any sort of piece of text, and you feed the regex engine a pattern. So in this case, we have our little poem here, and then we're going to give it this pattern SEA. And what the engine does, it basically starts at the very beginning of the string, and it looks at the first character in the pattern and just asks if it matches. And if not, it moves on to the next character in the string. And so in this case, the S does not match the A. So it moves on to the next slot in the pattern, which is a space, performs the same test, not a match, move on and on and on. Okay, so then let's say the first character, or let's say the character in the string matches the first character in the regular expression. The next sort of decision tree that the engine goes through is moves on to the next character in the pattern, which is E, and the next character in the string, which is N. and performs that test. So does E match N? No. Then what the regex engine does, and this is fairly important, is it backtracks to the point of the last match. So it steps back to the S, and then it resets and moves on from there. So then we're looking at the question of whether N matches, we test the question whether S matches the N. Is it a match? No. It continues going. Then, of course, when it continues to match and the second character matches the second character in the pattern and so forth, all the way to the end of the pattern, then it registers as a match and it saves the location, the position of those characters, the start and the end, and then moves on from there. So that is, in a very basic sense, an intuitive sense, what's happening under the hood. Of course, the trick is choosing that pattern right. So you can do a lot of variations. In this case, it was just a one-to-one match. I want this word. Where is this word going to match in my string? But you can tell things like, instead of an S, you could say, I want any sort of generic character that's a letter or a capital letter or something like that. So I think that's what I hope to go over the basics of that in the next section. Any questions about that part? Okay. So in R, there are a couple of pretty important functions that I could think of that use regular expressions. The big ones, and there could be more. Actually, if anybody knows any more, please chime in. But grep and grep-L, which is like a logical version of grep. What this basically does is takes the first argument is a pattern. The second argument is a string or a character, a vector of strings. And for each item in this vector, it tries to match your pattern to that string. So in this case, we have a vector of characters, which are nuts, and grep is going to try to match the character S to each one of these items. So it starts with peanut. There's no S in peanut, so it doesn't give anything. Moves on to hazelnut, cashew nut, macadamia nut, and the only item which it actually matches is cashew nut because there's an S in there. And so it returns the index of that item. So the third out of this vector. One important parameter for grep is also you can set the value equals true. So instead of returning just the index 3, it'll return this character or this string. So it'll return cashew nut. There's some examples of that below. And then grep-L is just the logical version of that. So instead of returning the index, it returns a vector of the same length as your original vector with false or true. Did it match or not? Okay. This is like an extremely simple but very useful function that just comes up all the time. And this is often found in this other function that comes up a lot when you're messing around with files and file names, is list files has an argument pattern, which is basically a regular expression pattern. So it will search, it'll list all the files and only return the files that have a match with your pattern here. So in this case, I looked at my files on my computer and it returned only the folders, I guess, that have program in them. How many, so everybody, some people have used grep before? Yeah, okay. Sub and gsub, these are kind of another step forward. So in this case, not only do you find a match, but you within that string you replace whatever's matched with what you choose. So the first argument is your pattern that you're going to search for. Second argument is what you want to replace the match with. And the third argument is a vector of strings. So in our case of the nuts, we can replace any a, lowercase a, with a capital A in this case. So pretty straightforward. G sub. Okay, so how about for you guys are probably reviewing this, but just based on this, can somebody tell me what the difference is between sub and G sub based on the output of it there? Maybe somebody who hasn't.
First one.
And then G sub would be all of them, right? So it's just sort of a generalization of sub. Sub that only does the first match. G sub does all matches. Okay, because we can see here in macadamia all the A's are replaced. All right, then we're getting a little bit more fancy here. Regexpr and Gregexpr. These return vectors with a lot of data, more data about the matches. So it returns the starting position in the string and the length, I believe. Yeah, the length of the match. So, and again, the one regexpr just returns the first match, and gregexpr returns all matches. So if we look at, if we run this with our nuts example, the first match starts at the position 3, so the third letter in that character, or in that string, and its length is 1, and then so forth. Whereas gregexpr returns a list, which is slightly different, one for each item in our vector of strings. And you'll notice that all of the first 3 have a single match recorded, whereas the fourth one has 4 different matches corresponding to the 4 A's in this string. So those are the starting locations and lengths, etc. And then regexec is another modification on this sort of theme where we're using capturing groups. So I'll talk a little bit about that in a second. But basically, parentheses. Those are parentheses, right? The circle. Okay. Yeah. Not only does it return matches, but it returns these sort of groupings within your matches. So you identify groupings with parentheses. So in this case, our pattern is these 3 groupings. And if we run this function across this string, it will return the full match, and then the match of the first group, second group, and third group. And I didn't have the output of this actually, but maybe we can just see what this looks like, what it returns in raw form. So yeah, these are the starting locations of each of the matches. The first match is 13 characters long, so it just matches the whole string. Second match is 6 characters long, and it just matches the first part here, then the space, then the third. Okay. And another function I've used here is this function called regmatches, which takes the output of regexec or regexpr that returns all this information about these matches and actually just returns the strings that it kind of matches to. So you can see in this case, we looked at the result of our regexec, and it returned, the first match was Harlan Pepper. Second match, which corresponds to this first group, Harlan, then the space, then Pepper.
So it just broke down the single match into each token?
Yes. Yeah. So yeah, each one of these would be a token. Right. Questions about that? What's going on there? We'll go into the groupings a little bit later. I talked about list files, has a function pattern or an argument pattern, which is useful. String split, another really useful function, takes regular expressions. So if you have just a big, really long string with some pattern that repeats, and you want to split it up into a vector of multiple strings, you can use string split. And then agrep is another useful one I've come across, which is a kind of smooshy version of grep. It kind of is has more relaxed matching criteria. So strings are sort of similar. It will match, which is pretty useful when you're sort of merging data sets sometimes.
So is that like an umlaut doesn't matter, or is it?
Yeah, it's
about like A versus O not matter.
It's it uses something called the Levenstein distance. That's basically how many insertions or deletions in a string does it take to go from one string to another, like the minimum number of character changes, and it has like a set threshold for how many changes are okay. You can change that threshold. So, and I think there's an example of this later. Any other functions anybody's come across that use regular expressions? Yeah.
So I'm just wondering, is there a version of grep minus I, like a ignore case, or a case insensitive version, or is that a parameter to the regular grep, or?
Yeah, I think that's a parameter to the regular grep. Ignore case. Yeah, should be. Yeah, ignore case. So that's in the case where you want your pattern to ignore capital letters in the matching criteria. So that's a useful little argument. You could also just use a function to lower, which is just take all your capital letters in your string and make them into lowercase, and then make your pattern lowercase too. I kind of try to, whenever I do stuff, I try to like make them as like dumb as possible, just like single step, rather than combining multiple steps and making really complicated pieces of code. So, I mean, this will probably be not very as fancy as can be done, but I think there's a lot of advantages to keeping things simple. Okay, so those are the basic functions in R. Let's talk a little bit about some of the syntax for regular expressions themselves. So regex are kind of like a programming language in and of themselves. There are these special characters which have different meanings when you pass them in as regular expressions. So, and these are called meta characters or special characters. And so if you try to just pass them in as themselves, let's say you have, so for example, here's our first meta character, it's the caret. And we try to match a string, the caret. Grab caret string. That shouldn't be.
It's finding the wrong thing.
Yeah. Okay. Yeah. That's a bad example because caret means beginning of line. Let's do. Let's give another one.
Like if you were trying to match the or operator, would it find it or not?
Yeah, let's try that. Found that. Okay. Well, we maybe think of a better example here. On this, I can't do it on the spot, but basically,
Maybe do a G sub to show where it's finding it.
oh, good call.
I don't know what that's going to do with the pipe. So.
So, caret means, in regex world, it means beginning of the string. So it means a special character that signifies the start of a string, and it's the position like right here between the start and the first space. And so the engine goes along, and the first it looks for. Actually, this would probably work. But anyways, it looks for that starting character. It matches, returns a match. And in GSub, we inserted our match here in that spot. In order to actually match a caret, we need to escape it. We do use double escapes. And so the match happens where we want it to happen. So I was actually just thinking about a way that we could have we do space, or we do grab here. This would have been better if for the original example here. Okay, so it doesn't match, right? If we had a space, because it can't find. This is really meaningless as a regular expression because you're not going to have a space before the starting of a line.
So why do you have to double escape it? Why not just one side?
That is because escape is also, the backslash is also a special character for R. And so you need to tell R not to interpret that backslash by backslashing it.
The funnest is searching for a backslash. I think it takes 4 of them.
Yeah, yeah. There's an example of that I put up, but it's just like
Okay.
inception of backslashes that happens. It's pretty insane. Okay, so likewise to the caret symbol, we have $symbol, which is just the end of the line. So this can be helpful, I've found, when looking for things like file names, where you just want to look at the extension, and maybe there's, just to be safe, maybe the file name has some sort of extension name it. I don't know if that's really realistic, but so this looks for anything that has CSV and then end here, and it doesn't match this CSV or this CSV, but it matches CSV. Okay, dot is another special character to watch out for. It's probably the most important one that you don't want to mix up because it matches anything in R's version of Regex. So we have a bunch of these strings, some special characters, some characters indicating like a new line or a tab here, which R. That's how R interprets this symbol, and it matches them all, except for this empty character. So you want to be careful about these. The way that you would actually look for a dot, probably the easiest way, and I'll talk about this a little bit, is to put it in brackets. So one important thing about these brackets is that anything in brackets, special characters lose their meaning inside them. So except for a couple, but so if well, let's keep moving. I don't know. Maybe I don't know LaTeX very well, but
It's not a comment character.
I'm not sorry. What underscore, whatever it is that you have to put in front of mathematical operators like and.
Oh, the dollar sign.
Yeah.
Kind of. It's like, yeah, it delimits a special set of string.
Or operator is another special character. We can look for. It looks for either this or this, with preference for the left-hand side. So here we're trying to find any string that has these characters or these characters. And the way that the Regex engine works is it will start traversing the string and on over here. And if it finds a match, it moves on. If it finds a match, it moves on, keeps going. And if it fails, like somewhere around here, then it will go back to the beginning of the match and try these characters. So that's generally how it works. These are brackets. So they define a character class. And so any character inside those brackets will match the single character. So in this case, we have a vector of strings, maybe some like file names from outputs. And when we put these two characters in brackets, anything that matches this part and then has either an A or a 1 will match. So of course, this character matches as well as this string matches.
So that's sort of just like an abbreviated or, right? Or
in a way,
easier way to do it.
But it comes in handy when you have cases like this where you just like, I want a number between 0 and 9. You can use this dash, and so this will pull out any character that is a number, basically. You can do the same thing with letters. So any lowercase letter from A to Z, any uppercase letter from A to Z, or any number in this case. And it doesn't have to be A to Z, it could be A to G or any sort of range. And you can negate. This is a helpful method. So inside of brackets, if it starts with a caret, any character inside the brackets will not match. So this is basically asking, find me a match that has run in it, followed by any character that is not 1. And so all these 3 match. So given these sort of little tweaks, it's important to note that most meta characters lose their meanings inside brackets. So they will actually be literally searching for whatever you put inside them, except for these 3. So the caret, the dash, and the backslash. And there's ways to include these inside the character classes, but I'm not going to get into it right now. Curly brackets define how many times something should be repeated, how many times what precedes it should be repeated. So if we have a string that has a bunch of numbers that are of different lengths, this will look for, give me any number that's repeated 4 times and is bounded by start and end of a string. And of course, there's only one of these options that match that criteria. Just that. You can also do ranges with curly brackets. So give me a number between 0 and 9. Starting, give low end of 1 character long, upper 3 characters long. And so that gives us first 3. And so, yeah, that can be pretty useful if you don't know how long if you're looking for a number and you don't know how many digits it will be, but you know it'll be a certain number of digits. For example, like a date. Dates tend to follow a pretty similar structure. So you can look for like numbers that are 4 digits long, and etc. Pluses are basically say, okay, take what precedes it, it will match it, find a match at least once, and keep matching as far as you can. So if we have a series of dates here, and our regular expression is find at least one number at the beginning of the string, and give me all the numbers that follow it. We apply that to this vector of dates. It should, I didn't actually print that. Let's do that. So it starts here. It finds the 1, it's a number, and it moves on to the next character. It's not a number, it stops. Starts here, finds it's a 1, moves on to the next character, finds it's a 0, moves on to the next character, not a number, stops. Starts here, not a number, doesn't match. Okay. Plus, so that's plus. Star is like plus, except it doesn't have to match once, so it's sort of a little bit more optional. So in this case, let's say we want to find something bounded by dashes that's a number, and we want it to be, we want all the numbers between the dashes, basically. In this case, the 1 matches, 25 matches, and then this matches because it's essentially optional. It matches 0 times, so therefore it returns. It actually qualifies as a match. Okay, any questions about that? Hopefully some examples will clarify that a little bit. So a note about these, the star and the plus, that's pretty important, is that these regex operators are considered greedy, meaning that if they can match, they will match. So you kind of have to be a little careful with them. So here's an example. We have this string, and we want to extract the letter between the quotation marks here. And if our regular expression is like this, we expect it to match something between the quotation marks, give me as much of it as possible, and then end the quotation mark, so between the quotation marks. But when we actually try to match it, it doesn't just give us what's between the quotation marks, it continues going until the regex, until the second quotation mark. So what's happening there? Basically, it finds the first match here, continues along to the quotation mark, then it matches the F, and because it has a plus sign, it's going to continue try to matching something. So then it matches the next character, which is a quotation mark. Because what we're matching it to is a dot, which matches anything, it says okay and continues. And then it matches the space and then and continues all the way to the end and comes back. So what we want to do is change that behavior in this case. So one way we can do that is by making the greedy operator lazy. So that means it won't continue matching if it can. It will only match once and then see if it can continue the rest of the regular expression. And we can.
In that first example, if it's matching any character, then why did it actually stop and not get the period in the space?
Okay, so that's a good question. And I was actually thinking about myself, and I think I just remembered the answer to that. So I think what it does is it travels all the way to the end. The dot matches all the way to the end. And then it reaches the end, and then it finds the end character of the $sign. And the $sign does not match the dot. So it takes a step back, and it looks at the space, and then moves on to the next character, which is the quotation mark, and the space does not match the quotation mark. So it takes a step back. It finds the dot and moves on to the next character, quotation mark doesn't match. And then finally steps on to back here and finds that the quotation mark does match. So is that?
I'll look at it later.
Yeah, I think I might need to explain that again, basically. So once the engine fails, when it's in this sort of greedy mode, it steps back one space and then tries the rest of the regular expression. So it takes up all it possibly can with this dot, and it fails at the end because it's trying to match a dot with the $sign. So then it steps back. Or wait, actually, it might not be that way. It might be matching the $sign and then looking for a quotation mark at the end.
Yeah. It needs a quotation mark at the end of the string that it's matching.
Right. So it goes all the way to the end. It looks for a quotation mark. It doesn't find one. Steps back. Looks for a quotation mark. Doesn't find one. Steps back. Steps all the way back to this point. Finds a quotation mark. Returns the match.
I got you. Okay.
Yeah.
Did you ask it explicitly to end the string with a quotation?
Yeah. So it must have that match.
Gotcha. Okay, that makes sense.
Okay. So to change that behavior, where it just continues matching, you need to use this question mark, which is another special meta character. So that basically means that instead of trying to match everything it can, it will only match as little as it can. So when the regular expression comes across here, it goes up to here, and then it finds this dot. It matches the F, and then it tries, instead of moving on to the next and trying a dot with the next character, it just steps on to the actual next character in the pattern and tries to complete the regular expression. So in this case, that's what happens. it matches the dot, and then it tries the quotation mark for the next character, which matches, and it's successful. Does that make sense?
You just use one.
Yes, you could. However, if you didn't know how long this character was going to be, you'd have to do something a little bit more fancy. But
This won't work either. The question mark.
what's that?
If you didn't know the length of the F,
Yes.
so this won't work.
Okay, so if F was longer, then it should get that as well. So we could actually try that. Gee, I hope this works. Yeah. So what happened there was the dot matched the first F, then it tried a quotation mark with the second F, failed. So then it goes back and says, okay, I got to expand my dot. So it expands. Second F matches the dot, tries the quotation mark on the third F, fails, steps back, expands the dot, so forth until that part. I should mention at this point, like, I'm aware that this might not be super clear. So how I learned all this stuff, I have a link to this website, and it explains regex in like pretty clear detail. So I think it's worth just really reading through this. It doesn't take that much time, and I think it can be really helpful. And it also has a really nice explanation of how things work. And that case that I just was talking about, there's an example of that is gone through in pretty clear detail too. So.
And we'll put Steve's presentation with the links to that other page up on the DRUG website.
Cool. All right.
Hey, Steve, could you just mention briefly what you used them for?
Yeah.
And how you found them most useful?
Yeah, that's a great comment. So I've used them mostly for scraping data from the web and cleaning up scraped data from the web to download like an HTML page, and there'll be some sort of structure to the data, but it might be kind of variable across the different pages that you download. And so these are like quick, nice, one-off ways to clean up data. And actually, I have an example down below, which we can run through real quick. But is that how you would say you've used them, or do you other people?
Yeah, I haven't used them directly for that. I think trying to rename files, searching for certain parts of, say I have several types of code files, and I want to find where I've defined a function in every one.
Yeah.
Like that. I mean, I guess once you understand them, there's lots and lots of uses, but I was just curious if there were any particularly relevant for the type of ecological research you do.
Yeah. So I would say probably most of it, come most in handy when dealing with file names and cleaning up data, string character data.
I use them when filtering a data frame mostly. So like if I have a column of like station names and I want to filter based on a station name, but there are multiple stations, it's like Lisbon 1, Lisbon 2, Lisbon 3.
Right.
filter on.
Or slight variations.
Yeah, or slight variations, or like sample numbers are another big one because they're often randomized. But they have some sort of sequence that identifies them as being part of the class.
Yeah. Yeah, it's super useful for that stuff. Yeah, I guess we're kind of running out of time here, but
Could you show us the example?
yeah, I could just jump down to examples. There's just a couple more things here. So scraping web links actually here. So went to this website that has some solar radiation data. It's like a pretty old, funky website, so it's not easy to download things in bulk. So what I wanted to do was basically write a loop that would follow each of these URLs and download their contents. So using these libraries that interact with the internet and get URLs, I just pointed them to this main page, which displays this, and it basically spit out this big long string of HTML code. And so with just a little bit of knowledge about HTML, I can pick out the links basically. I just wanted to create a big vector of links to follow in this case. And so I see there's like a repeating pattern of this character return new line that seems to be within this big string. So first thing I want to do is I want to split this into a bunch of like chunks of other strings that I can manipulate and search. So what I did was string split and just basically cut this up into based on this string right there. And it gives me a vector where each item is aligned with that HTML code.
Steve, do you want to mention why you have that? Why you're taking the first item from the list there?
Yes, because string split can work on a vector of strings, and so it returns a list. And since my item has only one, I have only one string that I'm splitting, it returns a list of length 1, and I want the first item. And so the item, then each item in that list is a vector of the chopped up string pieces, if that makes sense. Is that what you would?
Yeah, just it always returns a list. So if you're giving it a vector, you just take the first item, the only item in that to get a vector back.
Right. So then I can just use simply, if I want to look for links, they all have this formulation href. So I can use grep to just pull out all the incidences of links. And then the links also are also all named info, the ones I want. So I want metadata here. I pull out those links and I get a series of strings that look like this. And what I really want is this little piece right here, which I can just loop through and download, or paste it together with my base URL, loop through and download each one of them. And so this might be a little bit more convoluted than it needs to be. Like, nice thing about Regex, like R, is that there's multiple ways to do the same thing. But so this basically says, all right, start at any character, match it as many times as you need to, but be lazy. So only match as minimal as you can before you reach this string href equals quotation mark. So I'll continue matching all the way up to here. It will see this href, start matching there. So with this quotation mark here. And now I have the parentheses, which is my grouping indicator. So it means capture capture and save whatever is inside this parentheses. So basically press record. So it starts recording here, and it says basically give me everything, anything, up until you reach .htm. So it's going to continue matching all the way up to here. Then it's going to match that HTM. This dot is totally superfluous. Followed by a quotation mark there. And then this just basically says, then match everything after that until the end of the string. And so this function is gsub, and it will take whatever matches. So in this case, it matches the whole entire string because I've set it up that way with these expanded matchers on either side. And I want to replace it with whatever was captured, my first capturing group. And so it will replace this entire string with whatever was inside the parentheses. I indicate that by this \\1, meaning the first group. If I had two capturing groups and I wanted to replace it with the second one, it would be \\2. And so it returns just that kind of cleaned up line of text. Now I have these URLs that you can put into a loop and download. And then there's a couple more examples, like with each one of these downloaded pages. Let's say I want to extract latitude, longitude, elevation. I can do a similar pattern where I split up the HTML into different strings. And then if I want to get latitude, I can do a similar process where I match everything up to a number that's either 1 or 2 digits long, followed by an actual period, followed by a number that's 1 or 2 digits long, and ignoring everything else. And I'll call that latitude. So in this case, it got this little piece right there. Let's say if I want, and then this, if I want to, I do want to know if it's north or south. So I can use this regex here to extract either an N or an S in this string here. Same with longitude, east or west. I can extract the name, country. It's pretty much a similar process, actually. And then one last example, really quick. This is a similar example to what Ifumi was talking about with station names. So say you have a bunch of different data sets with potentially duplicated stations, but they might be spelled a little differently or have different kind of coordinates on them. In this case, like a town in sort of eastern or western Thailand, which has all these different variations on the spelling. Say we can't, and we have like thousands and thousands of these different stations. So we want to try to make this as automatic as possible. This is an example that we're using agrep. So first thing I would do would be to take out all these special characters and spaces to try to make these strings as uniform as possible. I make them lowercase, take out dashes and dots and slashes and spaces. And this is what those station names look like. And then if we just use grep, so basically take every one of these and see if it matches any one of these. The first station does pretty well. It actually matches most of the others. But there's still one station name that doesn't match. It only matches itself. And so that's where agrep can be helpful, because agrep is, remember, this more flexible version of grep. So the string length doesn't matter. It can substitute characters and tries to find similarities. And in this case, I'm just comparing, using agrep to compare each station name to this difficult station name. And this shows that we find several station names that match that station. So then if I was like trying to pull all these together and make a big list of all stations that are identical to each other, this would be one way to do it. So that was a little fast. But this will, again, this will be on the website and perusal. I'll probably change it a little bit. But so yeah, concluding thoughts. There's a really nice application, web app to practice with these. So you can put like the text you're searching for in here, and it's nicely highlighted code that talks about different ways to formulate your regex. And then just my thought was, like in my opinion, rather than these things can get like really convoluted. Like you can make really fancy regular expressions, and it's probably better to just do a series of very simple ones and do all the complex stuff in R, like as much of the sort of manipulation as you can in R, but just sort of like do very simple, easily to read regular expressions, because human readability is often way more important than like elegance, I think, in terms of code. So yeah. Any questions or thoughts or?
So I have a question. So you were using that to lower command to make everything lowercase so you can classify it, right?
Mm-hmm.
What if I have data that's actually mostly uppercase? Can I make it everything uppercase or?
Yeah. Well, there's a function to upper.
Yeah. It's
So
the same thing.
that would do the same thing. Yeah.
I have a question. Why should we use the backslash? There are two backslash before a symbol, which means the beginning of the string.
Yeah. So that was the case where if we wanted to actually look for a caret symbol in our pattern, like if our string had an actual caret in it, we want to search for that, we have to escape it, which is what we do with the backslashes. So we need to tell the regex engine, don't treat this caret as a special character, treat it as an actual literal caret symbol, and look for that in the string. And the reason we do two backslashes is because the backslash is a special character for R, and so we need to tell R to ignore that backslash, and we do that with the backslash. So.
In another example, there are two backslash and together with a one.
Yeah. So in another like programming language, that would just be a single backslash and a one to refer to that first capturing group. But again, because it's R, we need to tell R to ignore the first backslash. We double backslash it.
I mean, in another example, there are two backslash and a one.
Yeah. Let's see. Capturing groups. Yes, right here. Right. So that the regular expression symbol, like the generic across platforms, it for the first capturing group is \1. That's like a special character, and that refers to whatever's inside the first parentheses. \2 refers to whatever's in the second parentheses if there's a second group. And the reason there's two backslashes is because we're doing this through R, so we need to format it correctly. So I think like most things, it's not really gonna like sink in until you have an application for yourself. and do some like Google searching and stuff like that. But it's not so bad. Like, not too bad to learn, I found, and really useful, and like kind of fun in some cases, like a little puzzle. Like what's the best way to match this pattern that I see over and over? Because sometimes you'll get too much, or sometimes you'll get too little. And, yeah.
Thanks, dude.